Let's talk about another form of regression called logistic regression. Logistic regression can be thought of in the same terms of linear regression, but it's for binary or yes or no problems. So if we're trying to predict whether something is in one of two classifications, is this a stop sign or isn't this a stop sign? Is this a boy or is it a girl? Whatever it is, that's where logistic regression can be a useful tool. It can predict whether things are yes or no or one thing or not based on the training data you give it. So it's like linear regression. The main difference is that the final predictions that come out are not a prediction of some linear value, but they're transformed into a range between 0 and 1. And then we can translate that value, that predicted value between 0 and 1, into a yes or no prediction answer. The way we do that is through something called a sigmoid function. And this is where logistic regression gets its name, because another name for the sigmoid function is the logistic function, hence the name logistic regression. But again, don't get hung up on the names here. It can be confusing. It has nothing to do with logic. It just is the name of the function under the hood. So fundamentally, logistic regression is just binary classification, okay? That's it. It's a way of doing binary classification, one thing or another. This is what that sigmoid function looks like. So this allows us to transform our final predicted number, which is between 0 and 1, into some other function here. And the way it works is that if it ends up above 0.5, we can predict a 1. And if it's below 0.5, we can predict a 0. What's actually going on here is that it's translating the output of logistic regression itself into a probability of it either being 1 or 0, yes or no, or it is this thing or it isn't this thing, whatever your binary classification problem is. So by taking that output of the logistic regression itself and applying the logistic sigmoid function to it, we can very easily translate that into an actual probability of it being yes or no. And if it's more than 50% probability, we can go with yes. If it's less than that, we'll go with no. So that's all the logistic part of logistic regression is. And we actually use this same logistic sigmoid function within the world of neural networks as well when we're doing binary classification problems. So this will come back later in the course. It tends to be called the sigmoid function there, but remember, it's the same thing that's happening in logistic regression. A couple of other things that are unique about logistic regression. Least squares doesn't work with the logistic curve, so we have to use gradient descent instead with maximum likelihood. And again, this ties into modern neural networks as well. So in neural networks, we tend to use gradient descent, and we often use the sigmoid function as well when we're doing binary classification. Anyway, the idea is that through gradient descent, we're just iterating to try to maximize the conditional probability of y given x. So y would be the thing that we're trying to predict. X is the thing that we're giving it to predict it with. And we're just trying to maximize that conditional probability through the process of gradient descent to converge on the best logistic regression model for our data. Let's see it in action and dive in with some real data and apply logistic regression to it.